Hello, my name is Caleb Svensson, and today I will be talking to you about the Golden Gate Bridge. The Golden Gate Bridge stands as an incredible feat of engineering achievement for the following reasons. Reason one being its design. It was the largest suspension bridge of its time, with a center span of 4,200 feet and a total length of 8,981 feet. The cost being the second reason, with an initial proposal cost of $60 million being reduced to one of $17 million under the engineering of Joseph B. Strauss, this marked a significant historical achievement. And reason three being its structural significance. Having been constructed with state-of-the-art engineering and also being a suspension bridge with curved backstays, a relatively new technology for that time. The Golden Gate Bridge's iconic status. A parallel can be drawn between the Golden Gate Bridge and the civil engineering disciplines of earthquake and structural engineering. As the fields of structural and earthquake engineering have evolved, so did the bridge itself as to exhibit engineering achievement and its iconic status. The trusses and lateral bracing. The trusses of the bridge are 25 feet in length and 90 feet in width. They are composed of top lateral bracing and new bottom ductile lateral bracing constructed in 1950. These trusses are connected to the towers and pylons through rocker links that transfer vertical loads and lateral forces. This helped ensure the structural integrity of the bridge in the event of an earthquake. The new ductile bracing improved upon the previous bracing by now allowing for the bridge to withstand high winds and aftershocks. And as we can see in figure 1, here is an image of a truss in the location of the braces. The previous bracing. This bracing was composed of riveted connections. Previous lateral bracing consisted of silicon steel box cells composed of 45-degree angled members on all four sides. Under large amounts of stress, the corner angles of the bracing are prone to buckling because of inelastic deformation. In the event of buckling, the bridge would still allow for traffic to continue because of the innovative engineering principles behind the bridge's construction. And in figure 2, we can see the pre-existing bracing. And in figure 3, we can see the location of the buckling in the event of an earthquake. Now for the retrofitted bracing, this new ductile lateral bracing allowed for the bridge to once again exemplify structural significance by resisting aftershocks and high-speed winds, satisfying principles of aseismatic design. This bracing used tubular cross-section members to maximize efficiency and reduce stress, which in turn negated deformation. The new bracing would allow for the total elimination of overstress in the event of an earthquake. The bridge exhibited uniform and continuous distributions of strength and stiffness throughout its top and bottom bracing. In conclusion, these retrofits were not enacted because of a fault in the bridge's design, but yet to continue the bridge's engineering achievement into the modern day. This is why the Golden Gate Bridge is considered to be one of the greatest historical monuments of civil engineering, and how it serves as an iconic symbol for the field of structural engineering, showing how the civil engineering disciplines evolve, as do the structures and technologies behind it. Here are my references, and thank you.